All right, so we're going to talk about entropy. So 15.6 is about entropy. And the second law of thermodynamics. I hate when this does this. And so remember that for Carnot's engine, we said that the ratio of the cool heat over the high heat was equal to the ratio of the cool reservoir temp and the high reservoir temp. Okay? Well, if I just do a little algebra on that, I can actually end up with that the cool, doing some cross multiplying and dividing and moving some things around, I get these two ratios of the cool heat, which is not the actual correct term, and the cool reservoir is actually equal to the proportion of the high heat and the high temperature reservoir. Okay? So now I should point out this is for any reversible process. Not all processes are reversible. Okay? So these are absolute values, and the heat transfers from the cool temperature reservoir to the hot temperature reservoir. And so this ratio of heat over T, in general, heat over the temperature, right, is defined as entropy, or the change in entropy. So change okay. And in other words, that delta S, the change in entropy, is equal to Q over T. And this is for reversible processes. Okay? Where Q is the heat transfer, which is positive for heat transfer into the negative for heat transfer out, right? So we're talking about systems, positive, negatives, positive going in, negative coming out. And the temperature is the absolute temperature in which the reversible process takes place. The SI unit for entropy is joules per Kelvin. So this is going to be joules per Kelvin, right? And it's a good approximation for small changes in temperature. The definition of change in entropy is strictly valid only through reversible processes like Carnot's engine. However, we can find delta S precisely even for real irreversible processes. The reason that there is entropy S in the system, like an internal energy, depends on the state of the system, not how it reached that condition, but entropy is a property of state. right? So thus the change in entropy of a system between state 1 and state 2 is the same no matter how the change occurs. So we just need to find or imagine a reversible process that takes us from state 1 to state 2 to calculate the change in entropy. And so let me put, I'm going to put a graphic here on the screen. Give me a second here, I got to copy it. So this is what it looks like for a reversible process. So it doesn't really matter what's going on, okay? So for the reversible, where's my little thing here? So for the reversible process, in green, let me get a little green thing here. The reversible process in green, we have state 1, and then there's some sort of heat transfer to state 2. And then that change in entropy is just calculated by Q over T. However, in an irreversible transfer, it doesn't matter if it can go back or not. We could still calculate it, but now we have to find the change is irreversible. It's equal to the reversible, but we're really measuring state 2, the entropy minus state 1, okay? So when the system goes from state 1 to state 2, the entropy changes the same amount whether the hypothetical reversible path is followed or a real irreversible path is taken. So now let's think about the change in entropy in Carnot's engine, where the heat reservoirs for one cycle. The heat reservoir has to lose entropy, right? So let me slide this down, and we're going to write some more stuff. And I don't know if I need to draw the whole picture. But remember, for Carnot's engine, okay, you had a change in entropy which was equal to negative the heat over the temperature of the hot reservoir, okay? So this was a loss in entropy because the heat transfer occurs out of, remember that when heat transfers out, Q has a negative sign. So you have TH, I'll start to draw this. This is TH, right? Down here we have the temperature TC. You have Q, H, that's QH, the heat. And then we have this is QC. And then we defined our system as this. And then there was, you know, you could have work coming in or going out, but generally we would talk about work going out. So this could be work. And going into the system, going in was positive, right? And coming out of the system, you were taking heat out of this internal, which was negative. And so when they say, now let's take a look at the change of Carnot's where it was one full cycle. So the one full cycle, and we reverse this process for a refrigerator and all that stuff. So if you have, sometimes over here we would have heat that came out. So if the heat came out, that would be negative because it would be leaving the internal. Remember, the internal is all this stuff inside here, the internal energy. So anything that's leaving or coming out depending on the cycle. So this negative means that it's going out. Okay. And that's from the reservoir too. So think of it, this temperature, we have a temperature, whatever that is, if heat is coming out of this. So in other words, you could think of this as a separate system. And so this temperature has to lessen if heat is going out of it, right? And so that measurement between the heat coming out over what your total temperature is would be what we consider the change in entropy. All right. Likewise, you're going to have a similar situation. Oops. Oh, I hate that. But down here, if we think of this as a separate scenario, the heat going into the cool, we have this QC is coming in to the cold reservoir, all right? And they both have temperature and heat energy, all right? And so what does this mean with regards to entropy? So it means that the entropy, the total entropy, is equal to delta SH plus delta SC. So the entropy of the cool reservoir, heat ratio, and the heat ratio of the hot. All right, so what does that mean? Well, we also know that the entropy for this and the entropy for this, in other words, my total entropy, if I substitute these values in, are going to be QH over TH. And remember, we're talking about stuff going in and out, so at some point we might have to assign positive and negative values to our heat, depending on if it's coming or going, right? But this should equal 0. And let's talk about that. We are going to lose some energy here. Let me find a color. We'll use orange. So I have some. This has a temperature. This reservoir has a temperature, but I lose a little heat energy going this way. Some stuff takes place, and then that heat energy comes into here. So whatever leaves here, if I completely ignore all this other stuff, right? If I completely ignore all this other stuff and I just focus on these two components, whatever heat energy leaves here should go into here. And so the ratio of QH over TH and the ratio of Q, they should be the exact opposite, the same amount. It's leaving here, going in here. If it was ideal, okay, it should equal 0. So the result in general for the total change in entropy for the system in any reversible process should equal 0, right? But let's do an example of this before we dive any further, okay? So let's see how this actually works in real life. Okay, so I'm gonna copy it, paste it, and then we'll talk about what happens in a real irreversible process. So we just created a perfect scenario where we didn't have to worry about heat or work or anything like that. Because in the real world, what we would have to do is we'd have to worry about the work and then friction and all that other stuff. So it's not going to equal 0. But for spontaneous heat transfer from hot to cold in an irreversible process, the total change in entropy is 4,000 joules. So I'm going to start labeling some stuff. 4,000 joules. The hot reservoir temperature is 600 degrees Kelvin, and this is what that would be in Celsius. And the cold reservoir is this, and this is what the temperature would be in this. And it says, assuming no temperature change in either reservoir. Oh, that's interesting. Okay. So, what's the strategy? Well, the first thing we know, and it's asking calculate the total change in entropy. So we have to calculate the total change in entropy, which we just said was the entropy of the hot reservoir plus the change in entropy of the cold reservoir. Okay. So in the next line, we're going to say, because this is leaving, we say minus QH. We have to attach that negative sign to this. And then this one would just be QC over TC. Okay? But now, remember that the total change in entropy is 4,000 joules, right? Well, that's the heat transfer. So 4,000 joules is leaving. So think of it like this. This is our temperature. This is our hotter reservoir. 4,000 joules of heat energy is leaving, but it's entering our cold reservoir. So that means I'm going to have 4,000 joules of heat energy, but it's negative. And then remember, this is 600 degrees Kelvin. So that's going to go over, oops, I'm writing all kinds of crazy stuff. 600 degrees Kelvin, and this should be 4,000 plus 4,000 degrees, but the cool reservoir is 250 degrees Kelvin. So this is the total entropy. Okay. And so if you do the math on that, this ends up becoming, this is negative 6.67 joules per Kelvin plus 16 joules per Kelvin. Which is 9.33 joules per Kelvin. Okay, so this is our final answer, the total entropy. So the increase in entropy for the system of two heat reservoirs undergoing this irreversible heat transfer, and I'm going to show you a diagram of it. We see that this means that there is a loss of the ability to do work because this entropy is energy per Kelvin. And so we're not able to do all the work. So this is going in a reversible process. This leaves and it comes in. An irreversible process, it just leaves, right? And so what does that mean? Well, the heat transfer in figure A, the first part, from a hot object to a cold object is an irreversible process because remember, spontaneously heat doesn't leave a cold reservoir to a hot reservoir. It just doesn't reverse that way. It goes from the high reservoir It always goes spontaneously from here to here. It never goes the other way around. So it's always irreversible when you think about it, because that's what it does spontaneously. And so that's an increase in entropy, but the same final state, thus the same change in entropy is achieved for objects of a reversible transfer. Now, reversible transfers are we'll dive deep into that, but for today we're talking about irreversible. So it's reasonable that entropy increases from heat transfer from a hot to cold, and since the change in entropy, which is QT, there is a large change at lower temperatures. Okay, the decrease in entropy of a hot object is therefore less than the increase of the entropy of the cold object, producing an overall increase, just as in the example that we just did. This result is very general. So I'm going to type this because I want to make sure it's a little easier for me to type this. So there is an increase in entropy for any system undergoing an irreversible process. And just the very nature of heat transfer, when we talk about spontaneous heat transfers, they're almost always spontaneous, and so that means this is always going to happen this way. Okay. All right. So with respect to entropy, there are only two possibilities. Okay. With respect to entropy, there are only two possibilities. Entropy is constant for a reversible process, and it increases for an irreversible process. There is a fourth version of the second law of thermodynamics. The total entropy of a system either increases or remains constant. Entropy never decreases. So let me paraphrase that. Entropy never decreases. It either remains the same if it's a reversible process, or it increases if it's irreversible. So let's write that down. Irreversible so it never increases. Never decreases. While entropy means that some of this energy is not available to do work. So let's revisit this. We're going to do one more example, and I think we'll be done with our notes for the day. And this is that we had to lead all the way up to this, but this is what you'll find on your this is an important part of your AP exam. As being able to calculate entropy and understand that entropy, basically any thermal energy transfer is not 100%. Because in order for the entropy to remain constant, it'd have to be some sort of reversible process, but spontaneous heat transfers always go from hot to cold. So that means that your entropy is always going to increase. That entropy is going to decrease the amount of work you could do. So any energy that you transfer, you're going to lose some of the energy. So another way to say this is no energy transfer is 100% efficient. Okay. So let's recap this. So calculate the work of a Carnot engine operating between the temperature of 600 degrees Kelvin and 100 degrees Kelvin. The heat transfer is 4,000 joules. Now suppose that the 4,000 joule transfer first from the 600 Kelvin reservoir to the 250 Kelvin without doing any work. That's important. Produces an increase in entropy above before transferring into a Carnot engine operating between 250 degrees Kelvin and 100 degrees Kelvin. What work output is produced. So we want to figure out work. That's the goal. All right. Okay. So this is where we got to go back. So remember that efficiency is equal to 1 minus the cold reservoir temp over the hot reservoir temp, right? So to find the efficiency of this, we're going to say 1 minus 100 degrees Kelvin over 600 degrees Kelvin. And I'm getting that information from up here. This is TH, and this is TC. Well, that efficiency is about 83%, right? So we'll say that the efficiency, if I do the math on that, plug it in the calculator, I get 833. Okay. And then if we want to find work, we can remember that also efficiency is equal to the work over the heat transfer, right? So if I want to find the work, I multiply this by Q, multiply this by Q, and I get my next line is that Q times the efficiency. Oh, we should probably say this is QH, right? The efficiency of this. So then my efficiency, and this is QH, this is QH, the hot reservoir, is equal to the work. Okay. Well, what was the thermal, what was the heat transfer? Well, the heat transfer was 4,000 joules times the efficiency, which is 0.833, and that's our work. All right. Well, if you do the math on that, that's about 3,333 joules of work. Not bad. Now this is just part A. This is what they were asking for part A. So, part A wanted to know the work. Let me reread this. Oh, part A, calculate the work output. And then they gave us a different scenario for part B. So part B, it says, now suppose that 4,000 energy transfer from 600 to 250 reservoir without doing any work. All right, so I kind of read that kind of fast, but we do the same thing for part B. We do the same thing. We remember that the efficiency of a Carnot engine, put C for Carnot, is equal to 1 minus TC over TH. But now we have a new TC and TH. And they said use, so the difference is and it's worded weird, they're saying the the high reservoir went from 600 to 250, and the cold reservoir is still 100 Kelvin. So that changes this efficiency really, because my cold reservoir is still going to be 100, right? But my warm reservoir is going to be 250. And so if I do the math on this, now my efficiency is 6. So again, my work is equal to the efficiency. Carnot engine times the heat transfer out of the hot reservoir. So same thing here, my efficiency is going to be 0.6 times the 4,000 joules, which should give us 2,400, I think, yeah? 2,400 joules. And so that's the difference, right? Well, you get much less work. So when you change the temperature, even though you're transferring the same amount of heat energy, when you change the ratio of the two reservoirs, you have a far less efficient or far more efficient. So your goal is to have those temperature differences between the reservoirs. If you want to do work, you're going to have to keep them kind of far apart. And so I'm going to kind of give you a scenario what this looks like. Oops, wrong one. So this is the scenario, what they're talking about. So if I have 4,000 joules of heat energy coming out, and I can crank out 3,300 joules, and then this plus this has to equal 4,000. So then the heat energy gets transferred into this. But over here, if I have 600 that goes into this, right, our entropy increases, and then the work that I could do, now more heat comes into this. All right. So what does all this stuff mean? Well, it means that there's a 933 joules less work for the same amount of heat transfer in the second process. This result is important. The same heat transfer into two perfect engines produces different work outputs. Okay? Because the entropy change differs in the two cases. In the second case, the entropy is greater and less work is produced. Entropy is associated with the unavailability of energy to do work, right? So what they're saying is you have this 4,000 joules comes into this secondary heat reservoir that is regulated at 250 degrees, and so the heat transfer goes this way, and so you're able to do less work. So this will have a greater entropy, because your entropy by definition means that you're not able to do work. So a Carnot engine working between 600 and 100 Kelvin with a transfer of 4,000 joules performs 3,333 joules of work. But for the second figure, B, 4,000 joules is only able, because it transfers, the first transfer occurs, and that's into a 250K reservoir, but that's irreversible. Okay? So because that's irreversible, even though it goes into the Carnot engine, our entropy is increased because the amount of work we could do is decreased by 933. In other words, we were only able to do about 2,400 joules of work. So what does that mean? Well, we could talk about the work that's not available. And the work that's not available And there's an equation that we could use to calculate it. So the work that's unavailable, we'll just say can be calculated by the change in entropy times, this is not working right. I'm trying to hurry up and finish this. Times T0, where this is the lowest temperature utilized. So TO is lowest temperature utilized. The whole thing is annoying. Okay, so then what does that mean? Well, we calculated that our entropy was 9.33 joules, right? Times the lowest temperature. Our lowest temperature was 100 degrees Kelvin, right? And this is joules per Kelvin. And so that meant that, this is so annoying. Okay, and that's what we found. That was the difference. That was what we calculated. So one of the things that we talk about a lot in physics is the heat death of the universe. So basically, because heat energy transfers from the highest temperature to the coldest temperature, it's not reversible, right? So because it's not reversible, you have this loss as heat transfers from one object to the next, to the next, to the next. It's always going to the colder item, to the colder item, and that generates entropy, which means we can't do work with that energy. We're constantly losing some of this entropy to basically every time that there's a heat transfer. So let's do a scenario of this real quick. I'm trying to hurry before the bell rings. All right, so we're being asked, this is one, I think this is the last example. Find the increase in entropy of a 1 kilogram chunk of ice originally at 0 degrees Celsius that's melted to form water at 0 degrees Celsius. So remember that our change in entropy is equal to Q over T. And remember that Q, this we're going way back, is related to M LF, right? Where M is the mass and LF is the latent heat for fusion. For water, LF, so we're going to have 1 kilogram, and for water, LF is going to be 333 or 334. So our heat energy for melting ice is going to be 3.34 times 10 to the 5th power joules. Oh, this is kilojoules. This is kilojoules. That's why we have the extra stuff. So then, now that we know what that is, our change in entropy is 3.3. 3.34 times 10 to the 5th over T. But we said that this is 0 degrees Celsius, but in Kelvin that's 273 degrees Kelvin, right? So then if you do the math on that, our change in entropy is equal to 1, oh, this is annoying, 1.22 times 10 to the 3 joules per Kelvin. And that's it.